Okay, Michael, so we talked a little bit about the curse of dimensionality, but I think it's worthwhile to talk about some other stuff that comes up. We've been sort of skirting around this and bringing it up in various ways throughout our discussion so far. But I think it's worthwhile kind of writing them all down on a slide and trying to think through them for a little bit. So the other stuff that comes up in KNN mainly comes up in these sort of assumptions we make about parameters to the algorithm. So the one we've talked about probably the most is our distance metric. Our distance between some x and the query point q, and we've explored a couple. We looked at Euclidean, and we looked at Manhattan, and we even looked at weighted versions of those. And this really matters. So I've said this before, but I really think it bears repeating, that your choice of distance function really matters. If you pick the wrong kind of distance function, you're just going to get very poor behavior.
So I have a question about these distance functions. So you mentioned Euclidean and Manhattan. Are there other distance functions that the students should know, like things that might come up, or things that they should think of first if they have a particular kind of data?
Yeah, there's a ton of them. I think. Well, first off, it's probably worth pointing out that this notion of weighted distance is one way to deal with the curse of dimensionality. You can weight different dimensions differently, and that would be one. And you might come up with sort of automatic ways of doing that. That's sort of worth mentioning. But you'll notice that both Euclidean and Manhattan distance, at least as we've talked about them, are really useful for things like regression. They're kind of assuming that you have numbers and that subtraction sort of makes sense. But there are other distance functions you might do if you're dealing with cases like, I don't know, discrete data, right? Where instead of it all being numbers, it's colors or something like that, right? So your distance might be mismatches, for example, or it might be a mixture of those. In fact, one of the nice things about KNN is that we've been talking about it with points because it's sort of easy to think about it that way. But this distance function is just a black box. You can take arbitrary things and try to decide how similar they are based on whatever you know about the domain, and that could be very useful. So you could talk about images, right, where you take pictures of people, and rather than doing something like a pixel by pixel comparison, you try to line up their eyes and look at their mouths and try to see if they're the same shape, things like that, that might be more complicated and perhaps even arbitrarily computational to determine notions of similarity. So really this idea of distance and similarity tells you a lot about your domain and what you believe about it. Another thing that's worth pushing on a little bit is how you pick K. Well, there's no good way to pick K. You just have to know something about it. But I want to think about a particular case. Well, what if we end up in a world where K equals N?
Well, that would be silly.
Why would it be silly?
Well, so if k equals n, then what you're doing is you're taking, so in the case of regression, for example, you're taking all of the data points and averaging the y values together, basically ignoring the query. So you end up with a constant function.
But that's only if you do a simple average. What if you do a weighted average?
A weighted average. So the points that are near the query are going to get more weight in the average. So that actually will be different. Even though k equals n, it will be different depending on where you actually put your query down.
Exactly. That's exactly right. So, for example, if I have a little bunch of points like this, say, where you notice it kind of looks like I have two different lines here, if I could pick a query point way over here, all of these points are going to influence me as opposed to these points. And so I'm going to end up estimating with something that looks more like this, because these points over here won't have much to say. But if I have a query point that's way over here somewhere, these points are going to matter, and I'm going to end up looking at something that looks a little bit more like this than like that. Now, I'm drawing these as lines. They won't exactly look like lines because these points will have some influence. They'll be more curvy than that. But the point is that near the place where we want to do the query, it'll look to be more strongly influenced by these points over here or these points over here, depending upon where you are.
Well, that gives me an idea.
Oh, what kind of idea does it give you?
Well, what about instead of just taking a weighted average, what about using the distance metrics to pick up some of the points and then do a different regression on that subset of points?
Right, I like that. So we can replace this whole notion of average with a more kind of regression-y thing.
So it actually, instead of using the same value for the whole patch, actually still continues to use the input values.
Yeah, so in fact, if average is just a special case of a kind of regression, right? Right? So this actually has a name, believe it or not. It's actually called locally weighted regression. Yeah, so this actually works pretty well. And in place of this sort of averaging function, you can do just about anything you want to. You could throw in a decision tree, you could throw in a neural network, you could throw in lines, do linear regression. You can do almost anything that you can imagine doing.
Neat.
Yeah, and that works out very well. And again, it gives you a little bit of power. So here's something that I don't think is very obvious until it's pointed out to you, which is this notion of replacing average with a more general regression or even classification function actually allows you to do something more powerful than it seems. So let's imagine that we were going to do locally weighted regression and we were going to do, in fact, linear regression. So what would locally weighted linear regression look like? Well, if we go back to this example over here on the left, basically you take all the points that are nearby and you try to fit a line to it. And so you would end up with stuff that looked pretty much like this. While you're over here, you would get a line like this, but while you're over here, you would get a line like this, and somewhere in the middle, you would get lines that started to look like this, and you would end up with something that kind of ended up looking a lot like a curve. So that's kind of cool because you notice that we start with a hypothesis space of lines in this locally weighted linear regression, but then we end up actually being able to represent a hypothesis space that is strictly bigger than the set of lines. Right? So we can use a very simple kind of hypothesis space, but by using this locally weighted regression, we end up with a more complicated space that is complicated, that's made more complicated depending upon the complications that are represented by your data points. So this results, this sort of reveals another bit of power with KNN, which is it allows you to take local information and build functions or build concepts around the local things that are similar to you. And that allows you to make arbitrarily complicated functions.
Neat.
At least in principle. Okay, cool. All right, so you got all that?
I think so, yeah.
Okay, cool. So then I think we should wrap up.
Nice.
Nice.